Hi, Dr. Clark. I was hoping you could introduce yourself and tell us a little bit about your work at the Water Resources Research Center.
Yeah, David, thanks for having me on. So, my name is Eamonn Clark. I'm a postdoctoral researcher here at the University of Hawaii at Mānoa in the Water Resources Research Center. And what the WRRC is, if you're not familiar, is part of this nationwide initiative called the Water Resources Research Initiative that's run by USGS. So, there are centers or institutes like this throughout the US, total of 54 between the US and territories. So we have researchers working on all sorts of water related research questions: water security, cultural practices, water safety, water contamination throughout. Our center does both Hawaii and American Samoa. My research specifically, I work with Dr. Emily Marin. In her research group, we're focused on water treatment processes and disinfection byproducts that can form as a result of chemical water treatment processes. And then, specifically within that, my recent focus is on the disinfection byproducts that can form from drinking water sources that are contaminated with petroleum hydrocarbons, which arose following the Red Hill fuel spill, which you may have heard of a few years ago, where a Navy underground fuel storage tank leaked jet fuel into Oahu's aquifer and contaminated the drinking water supply for something like 96,000 people living in Pearl Harbor.
Wow, that's terrible. Yeah, I wasn't familiar with that disaster.
In regards to that, what we work on, the initial screening work was, oh, there's fuel in the water. We have to see the fuel. And we came in afterward and said, wait a minute, there's also potential transformation products. We need to see the transformation products. We need to see the disinfection byproducts. And to our knowledge, nobody's looked at the DBPs of fuel specifically. So it's been really interesting line of research, and we're hoping to have some manuscripts out the door on that before the end of the year here. Something to look forward
Oh,
to.
wow. That's great to hear. You had mentioned in your notes that you occasionally need to utilize a nitrogen evaporator in your research. I was curious what that workflow looked like. For instance, is that connected to like an LCMS?
Yeah, it is. So the work that we're doing is kind of trying to be as broadly analytical as we can. Of course, Dr. Marin could give you plenty more details about this, but part of my work, I'm learning how to do non-targeted LCMS analysis, and this is new for me, which is great for a postdoc to learn new techniques. So our non-targeted workflow involves solid phase extraction and then nitrogen blowdown to concentrate the sample further before injecting it on our LCMS and doing data-dependent MS2 with an Orbitrap.
Yeah, that's what I'm pretty familiar with in terms of evaporators like this are occasionally used for GCMS work as well, but LCMS, I would say, is
GCMS is coming.
yeah, that's good to hear. Previously, you were at the University of Utah, and I was curious what inspired you to develop the home built nitrogen evaporator. It sounded like in the acknowledgments that some colleagues actually asked you to build one for them.
Yeah, so let me tell the whole story in full. So when I was at the University of Utah, I was a PhD student in Mark Porter's group, and we were ended up toward the end of my time there. We started a project on PFAS analysis, and we were trying to develop a novel sensing methodology. And as part of that, we knew we'd have to be able to compare it to some sort of standard methodology. We were looking at drinking water, and we said, okay, so EPA method 537.1 is pretty much the standard for this. You could pick 533 or 1633 as well. We picked 537.1, and so part of my job was to set up our capacity to do that. So I had ordered all the parts for SPE. That's a little expensive to get set up with an SPE manifold and all those consumables. And then we said, oh, we also need blowdown. And we looked at it and we said, well, we don't have the budget for this. Now, I had done some stuff in the past, just some chromatographic sample prep where I tried a methodology that called for blowdown. And I had just taken a ring stand and some little 3-finger clamps and a few pasteur pipettes and rigged up like a 3-sample blowdown rig in our synthesis hood hooked up to a nitrogen line. And, that worked. But here we're looking at doing PFAS, doing LCMS. We need method blanks. We need instrument blanks. We need reagent blanks. We knew that our throughput was going to increase. And so we said we need some way to parallel this, but we don't have the money to buy one of those nice commercial systems that, for example, y'all at Organomation make. And so we said, okay, well, we have a collaborator in mechanical engineering. They have a laser cutter. We have a water bath. Let's figure it out. So that's how the project started. And then once we were into that, putting things together, our collaborators stopped by the lab and we said, oh, by the way, we're making this blowdown evaporator because we don't have one. They said, can you make us one? Because we need one for another project. So once I finished ours and had it working, they bought the parts and I helped them put together one for their lab. And then that gave us an opportunity to go back through and refine the design a little bit, find a couple of the sticking points. And actually, in the manuscript, we discussed 3 different geometries for different sample tubes. The one for the glass tubes, we have a nice picture of it there, had to be a special design because the tubes were different, and that was for their work. So grateful to them for giving us kind of the push to, hey, can you build this and see and refine our design? And then we realized, hey, this might be something other folks will find useful. So let's write a paper about it. So the technical note that you saw was born.
That's very cool. Yeah, I did note the 3 sizes that you commented on. And I would say that the 50 mil tube is probably the largest that I see our standard Enevap being used in. And for some people, what comes to mind is researchers who are deriving their work from 1633. That's just an example that sticks out in my mind from a lab I visited. In terms of the assembly process, would you say that 6 to 10 hours is a reasonable range for how long it would take to build something like this?
I'm always going to pad my estimates. I borrow from Mr. Scott. How do you expect to be a miracle worker if you tell the captain the truth? So I would say maybe more like 8 to 12 hours. But also, I'm going to point out that's going to be spread over like a week because this is a project that if you sit down and look at it, it's got a lot of hurry up and wait. So the first thing you got to do is you got to get all the parts, and then you have to laser cut all these individual parts. And you don't have to sit there with the laser necessarily, but the laser is going to take a couple hours. So that's an afternoon of putting in a sheet, cutting, coming back, changing sheets. And then once you start assembly, there's a lot of glue these couple of things, let it cure overnight. Yeah, realistically, it's spread over a week, but it's not that much actual hands-on effort.
Who do you see as the ideal candidate for a homemade solution? Obviously, budget's a big component, right? But my thinking was that it would be ideal for somebody where they don't have necessarily a constant use, but they might have a unique project with a limited term where it's, hey, we could build this and then use it for 3 months.
Yeah, I think you're right. So if somebody's just dipping their toe in and you're at that point where the smaller capacity solution, like I said, ring stand and some little pinch clamps and a simple little gas manifold won't quite do the trick for you anymore. So you need some more sample capacity, but don't have the budget, or you're not sure that this isn't just a one-off research project. Yeah, build your own evaporator and maybe it serves your purposes and that's that. You go on your way. Or perhaps you come down the road and you say, okay, like this worked for us, but we've beat it up. It's falling apart. We've been using it for a year and it's time to invest in a commercial product. I'm not saying it's going to inherently fall apart after a year. I do think it's a robust design, but like you say, I think it's a good entry level piece of equipment to have in the lab. Also a great way to introduce people to, hey, you can build lab equipment on your own. You don't always have to buy it.
Absolutely. And that goes nicely into the next question in terms of, I was curious what happened to the prototype, although it sounds like there were actually 2 units in operation.
Yeah, you could call them the alpha and beta or something. As far as I know, it's still in operation. So the collaborator who asked us to build the unit for them is actually my postdoc advisor now, Emily Marin. So she was at University of Utah, and then she got recruited to come here to UH Mānoa, and then she recruited me to come work for her. So the evaporator that I built with her graduate student at Utah stayed at Utah with him as he finished up his project with another faculty member. I think it's going to go into that faculty member's lab for whatever project they find. And then the original that I built in Mark's lab, as far as I know, it's just still sitting there in the fume hood for whenever somebody needs to do SPE and blowdown for PFAS analysis.
Yeah, that's great. I'm glad it's still working well for them and proves out the validity to the report in terms of it wasn't just to get through 6 weeks of a specific project. It's great that they can rely on it. On the RSC website, your technical note was included in what I thought was a pretty cool collection of reports titled Analytical Methods for a Low Resource World. I was curious, based on your experience in the lab, what other tools or processes do you see as attractive for other homemade solutions?
Yeah, that's a great question. This is actually something I've had an interest in for a while. So I, when I was an undergraduate at Central Washington University, I was working with Dr. Tim Sorey, and we ended up building a little home-built spectrometer using LEDs and a poster mailing tube to keep everything lined up, 3D printing some parts and buying some lenses. And so I think spectroscopic techniques, especially if you are just doing single analyte work, like that instrument, we were tuning it for the absorption maximum of a lead complex. I know there are folks like biologists who want to build a little fluorescence spectrometer to measure chlorophyll, and you only need, a certain excitation, a certain emission wavelength. So I think any spectroscopic equipment where you don't need full spectra and you don't necessarily need ultra high sensitivity is a great candidate for a DIY approach. Um, the other thing I think potentially is electrochemical methods. And with the availability of kind of DIY PCBs, so there's now software that's just available to the end user. You can go out and design your own PCB. You can send it off to this kind of bespoke company that will make you like a batch of 6 PCBs. You can build your own little potentiostats and start doing some electrochemical experiments. And I think for me personally, the thing that really interests me in this is the potential to build inexpensive DIY type of instrumentation that we don't really have Radio Shack anymore, but I'd like to think of something you could have built at Radio Shack, or you can buy the parts online, and that people can use to do citizen science and especially contaminant monitoring. There's a lot of folks have concerns about what's in my backyard, what's in this stream that runs by my house, what's coming out of this chemical plant that's upwind. So if we can build home build equipment that they can DIY, or that we can put together a kit for them and they can use that to do good science contaminant monitoring, that's potentially really powerful.
I totally agree. And I'm certainly all ears in the future if you're looking for a commercialization partner.
Yeah, we'll see where things go. Thanks.
But yeah, 3D printing has certainly impacted our business as well, mostly on the prototyping side for sure.
It was very nice when I was doing that project with Dr. Sorey. We were trying to build lens mounts. And so I could just CAD something up and take it over to our makerspace on campus and say, hey, run me a copy of this, will you? Come back 3 hours later, snap my lens in. That's not quite right. I need to change these dimensions. I'll pick it up from you tomorrow. It's such a fantastic technology.
What developments in terms of water research, whether it's related to PFAS or otherwise, should chemists be aware of?
That's a great question. And water research is a big field, and I'm still a new boy on the block. I'm doing my postdoc here in water research, but my PhD work was more bioanalytical immunometric assay development type work. I think one thing that really stands out to me is how impactful water research is to questions that impact people's everyday lives. And so this is probably not anything novel to say, but I think it's important, is that folks should be aware when you're doing water research, when you're touching this area, how much you can impact people's lives and how important this work can be to the average Joe. People hear about PFAS as a great example in the media. They hear, John Oliver on Last Week Tonight did a whole segment on it. You watch science YouTube, Veritasium did a whole kind of mini documentary on PFAS, and people are worried. So I think people should be aware scientists, that is, should be aware of that concern and look at ways that we can help with it. So I would say the big thing for PFAS specifically is we have these great methods. We have the LCMS-based methods, and we have, if you want to do total organic fluorine combustion ion chromatography methods, but these aren't accessible to the average person on the street who's concerned about what's in my tap water. So think about, maybe is there a way that you can either build a method that makes it possible for the average Joe to collect analytical results, or can you establish a community collaborative science project where you are using your instrumentation to help people answer these analytical questions? We have some ongoing community outreach work here at UH Mānoa through the WRRC, working with, for example, Dr. Aurora Kagawa-Viviani has a project with Native Hawaiian land and water stewards. And she connects with us and says, hey, I have these folks, they steward this land. It has this spring. They'd like to know, are there legacy or emerging contaminants in the spring? I think that's great, because it's, here's these folks doing their cultural practices, but they're concerned that this space might be contaminated. They'd like to have this information. Here we are, university researchers with the equipment and the expertise to answer that question about contamination. Let's work together. Let's provide that value to the community. So, like I said, maybe not exactly a novel thing to say, but I think what everybody should be aware of, especially in this space, is the impact your research can have, not just on the world, but on your local community, on your neighbors, that person down the street from you.
And it's an interesting area, and that's specific to PFAS. It's different regulations for different towns, different cities, states, and then at the federal level as well. There's certainly a lot of local commentary where every town is setting their own levels for what's allowed that might be a whole lot stricter than what the EPA, for instance, is saying is the maximum allowed limit.
I think that's a great thing to be aware of too. And that's something where scientists can really help the community to understand what's going on with regulation and what these limits mean. I mentioned the Veritasium video on PFAS. I thought it was a very powerful example where they went up to some sort of big in-ground tank or something. They said, look at the size of this tank. What is a part per billion? A part per billion is if I put like 1 drop of PFOA in so many of these tanks, and then a part per trillion is 1,000 times as many tanks. Helping people to understand what the concentrations mean, and to understand the regulations and the framework that is in place here. A hazard index like the EPA has is a complicated thing to understand, but we can maybe break it down and communicate it effectively to folks in the local community. That's a good service to provide.
I totally agree. I always like to ask at the end of each interview, what did we miss? Was there anything else from this technical note that you wanted to share with the audience?
That's a good question. I think maybe one thing we glossed over a little, we talked about the 3 different geometries for holding sample tubes that we talked about in the paper. The real takeaway we wanted people to have from that is not necessarily, hey, here's 3 laser cutting ready sample holders. If these work for your samples, that's great. The real takeaway I wanted people to have was, hey, you can design for whatever you're working with. And I put a couple of notes about that, like, hey, if you took this one and you shrink this hole here and shorten this standoff, I think you could use it for this type of thing. I just really wanted people to have what we did as an example, but then be able to take that, say, oh yeah, I can be creative. I can do this design. I can see exactly how this needs to work for my own application. It's not proscriptive, it's descriptive, right? So we're saying this is a thing we did and it worked for us, and in a similar vein, we think it will work for you. Come up with something cool, and I'd love to hear about it. I invite people, hey, you find our paper valuable and you design something based on it, send me a picture. I'd love to hear about it, because I just think that's neat in general when folks are able to make their own equipment for their specific bespoke process they're doing.
Absolutely. And one thing I'll send you is this was the first year where we actually did a best homemade evaporator contest, and we gave the winning lab a free unit. But that's something we plan on running in the future. And it's one of those things where there's a number of people, a certain percentage of labs where if you're just drawing a handful of samples a week, you could come up with a great homemade system that's perfect for your needs, or it doesn't make sense to buy anything.
Yeah,
So, but yeah, I think you might find some of the entries pretty exciting. So
that's
I'll
very
get those
cool.
over to you.
Yeah, that's cool. I look forward to seeing that.
Awesome. Well, Dr. Clark, I really appreciate the time today, and I'll include all the links we discussed in the description so people can check out the technical note further. Thanks so much.
Thanks again for having me and for working across the time zones to make this conversation happen. It's been great talking with you.
You as well. Thanks.